Let's start. We learned about base classifier. We learned about linear discriminant analysis and quadratic discriminant analysis. Basically, linear discriminant analysis is base classifier when you assume that your class conditionals are Gaussian, multivariate Gaussian. And you also assume that different classes share the same covariance matrix. Okay? Quadratic discriminant analysis is base classifier when you assume your class conditionals are Gaussian, but they don't share the same covariance matrices. Okay, so we learned about that. And we learned that in multi-class scenario, it's as easy as computing this quantity. I think we need a log here as well. Okay, we can compute this quantity for different classes and compare them. And decide for the label according to the value of this delta. Basically, we can assign point x to the classes which has maximum delta. Okay? So, but if you recall in the last lecture, I started to basically, expand this term because it's going to give us some insight toward LDA and QDA. So we considered a case in which sigma k is identity matrix. So in the case that sigma k is identity matrix means in the case that our data is spherical. So what's going to happen in this term? If I just look at this term, then I'm going to have x minus mu k transpose identity x minus mu k. Okay? And we notice that this is a squared Euclidean distance between point x and mu k. Okay, so this is squared Euclidean distance. Between x and mu k. Also, in the case that sigma k is identity, log sigma k is equal to 0. Because it's log of determinant of I, which is 1, and log 1 is 0. So just imagine for the moment that pi k is equal for all classes, so we have the same prior over different classes. If that's the case, in a very simple case that I have a two-class problem, each point, when I want to decide that this point x belongs to class 1 or class 0, simply I have to look at the distance and compare these two distances. The one which is shorter, this class belongs to that one. Okay? So in other words, I can say that my decision boundary is perpendicular to the point which connect mu1 and mu0. So this is my decision boundary between two classes if prior are the same. So any point on this side belongs to this class, any point on the other side belongs to the other class. If this prior is not the same for two classes, so if, for example, there are more points with label 0 than label 1, this decision boundary will simply, because of this bias, will shift toward one of these points. So for example, if I have 100 points here, 100 points here, this is going to be right at the middle. But if I have 200 points here with 100 points here, this decision boundary is going to shift toward mu1. So I have a prior over this class. I sort of favor this class more than the other one. Okay? So in this case, in the case that my class conditional are Gaussian and are spherical, so its identity, it's quite easy. It's just measuring distance between new point and the mean of each class. So let's consider the more interesting and more realistic case that sigma k is not identity. So let's see what we are doing in this case, actually. I believe you are familiar with singular value decomposition. So, but just as a reminder, let me write it here. As a reminder, you can decompose any matrix X, using singular value decomposition, SVD. You can decompose it as three matrices, U, S, V, transpose, such that U is eigenvectors of X transpose, and V is eigenvectors of X transpose X, and S is a diagonal matrix such that so any matrix can be decomposed this way. U is eigenvectors of X transpose, V is eigenvectors of X transpose X, and S is a diagonal matrix such that diagonal values are eigenvalues of X transpose or X transpose X. It makes no difference. So we can decompose any matrix using singular value decomposition. So let me decompose this covariance matrix using singular value decomposition. So if I decompose it using singular value decomposition, then this sigma k would be U S V transpose. But this sigma is covariance matrix. Covariance matrix is symmetric, right? Any covariance matrix is symmetric. So sigma is equal to sigma transpose because it's symmetric. If sigma is equal to sigma transpose, then sigma transpose is the same as sigma transpose sigma, right? So V is going to be the same as U because sigma is symmetric. So I can decompose it as U as U transpose. Is that clear? Okay. So let me look at this term, X minus mu k sigma inverse X minus mu k. Then sigma is US U transpose, so sigma inverse would be US U transpose inverse, which is what? Sorry? It is? It's U transpose inverse, S inverse, U inverse, right? But what's U transpose inverse? You know, in singular value decomposition, U is orthonormal and V is orthonormal. If you have an orthonormal matrix, the inverse of an orthonormal matrix is the same as transpose, right? So U transpose inverse would be U. Then it's S inverse, and U inverse will be U transpose. Okay, I can substitute this here. It's going to be X minus mu K U S inverse U transpose X minus mu K. Okay. So next step, I'm going to take this U inside this bracket and this U here. So it's going to be U transpose X minus U transpose mu K S inverse U transpose X minus U transpose mu K. S, if you remember, is a diagonal matrix. Okay, and when you take the inverse of a diagonal matrix, you basically need to reverse each diagonal element. I mean, if this is S, then the S inverse would be 1 over A, 1 over A2, and so on. Okay? So I can write it, you know, in this form. S to the power of minus 1/2 times S to the power of minus 1/2. Yes? Sorry? I can't hear you well.
You didn't write transpose for the
Here? Thank you. And here. Yes, thanks. Okay. So I have S to the power of negative half, S to the power of negative half. I will take this S to the power of negative half inside the bracket. So it's S to the power of negative half U transpose X minus S to the power of negative half U transpose mu K. I can do the same thing here. You know, if I take the transpose of this, since it's diagonal, the transpose would do the same as the matrix itself. So I would write just S negative 1/2 U transpose X minus S negative 1/2 U transpose mu K. Okay. So why we are doing this? You know, see what happened now. Look at this term. S to the power of negative half U transpose have been multiplied to X. The same term multiplied to mu K to X to mu K. I can think of this S to the power of negative 1/2 U transpose as a transformation, as a linear transformation, which has been applied to my data points and transformed them. So I can think that So it's a linear transformation, just call it T. T is S inverse, or I don't even call it T. So, you know, the transformation has been applied to points. So each data point X has been transformed by this transformation. So I apply this transformation to Hx and, you know, to a new space. It's a linear transformation. So if I map all of my points to this new space, the mean of these points will be transformed with the same transformation as well. Is that right? So if I map all of the points by a linear transformation, the mean will be linearly changed as well. Okay? So if I map all of the points using this linear transformation and pretend that this is my new set of data points. I had n data points, I transform all of them using this transformation, and now I pretend that I have n new data points in a new space. But this new data points in new space, what is their covariance matrix? Identity. So any data point that you give me, no matter what the covariance matrix is, you know, I can decompose the covariance matrix using singular value decomposition, find U and S, take half of the S inverse times U transpose, make a transformation, and apply this transformation to all of the points. No matter what the shape of this covariance matrix is, what's going to happen is the shape becomes spherical. Now we are back to case 1. So I can transform any data point, any set of data point, to a space such that I'm in case 1. Means they're spherical. So I'm back in case 1, and case 1 I know what's going to happen. It's just measuring distance between a point and the mean. Okay? So LDA or QDA in any space can be reduced to measuring the distance between a point and the mean of different class. Okay? So if you want to, let me show you this. I'm going to generate some points and then show you then when you apply this transformation, what's going to happen. You know, I define the mean of this point to be 1 and -1, and then I defined the covariance. This is my covariance matrix, and then, you know, MATLAB has a function MVN rand, which draw normal, multivariate normal points from, you know, a Gaussian which has this mean and this covariance matrix, and I said that I would like to have 100,000 data points. So if you look at X, you know, it's 100,000 by 2 matrix. To have the same convention that we use, you know, I would just take the transpose of this. Because we always treat data matrices as dimension by and d by n. Dimension by number of data points. So it's 2 by n. So 2-dimensional points, and they have 100,000 of them. Okay? So if I plot this X, this is basically, this 1,100 data points. You can see that the covariance matrix is like football shape. It's not as spherical, okay? But I can do singular value decomposition on this sigma. It gives me U S, which is diagonal, and it gives me V because of symmetric, V is equal to U. Okay. Now I can make a transformation, which is basically S to the power of -½ times U transpose. This is my transformation. If I apply this transformation to x's, the claim is that this x's becomes spherical. Okay? So I can multiply this to all of my x's. And I will call them nu x. Okay, now let's plot this nu x's. See, and let's do axis square. Okay. See, that was on the left was my data points. I applied this transformation, and now the covariance matrix is spherical. Okay. So you can do this for any data, make it spherical, and then you're in case one. Any question? Okay, suppose that I want to do LDA. A data set is given. Sigma k, which is common covariance matrix of these two classes, is not identity. For computation, I can do singular value decomposition, make it spherical, and then just measure the distance, add a prior to it, adjust it by the prior. Okay, you are giving me a new data point, so I want to decide this new data points belongs to which class. I have a transformation, which is s to the power of -½ U transpose. I apply this to my new data point. Okay. So now assume that we are not doing LDA, we are doing QDA. QDA, I have two different covariance matrices, sigma 1 and sigma 2. To make it spherical, I have two different transformations because I can decompose sigma 1 separately and sigma 2 separately. I have two different. A new data point as test point is given. You have to transform this point now and decide about this point. Which transformation you are going to apply to this point? Transformation that has been built based on sigma 1 or the transformation that has been built based on sigma 2? Sorry? You are going to do both. And then, how do you decide? Exactly. So basically, in the case that you are doing QDA, you have more than one transformation. But you can apply all of this transformation to your new data point and then measure the distance and compare them for each case. Okay? You're going to see the detail in your assignment because you're going to do that. Any question here? Okay. So one quick note about LDA and QDA, and then we are done with linear discriminant analysis and quadratic discriminant analysis. There is we learned how to do QDA, how to find quadratic boundary with the assumption that the covariance matrices are not the same. But there is a simple trick that you can make your boundary quadratic or cubic or, any order, and it doesn't have, this trick doesn't have to do with LDA or QDA in particular. It can be applied to, it can be used anywhere. So forget about classification for a moment. Suppose that we are doing a simple least square. You have been given X and you have been given Y labels. And I want to basically find a line here, I want to linearly map my X's to Y. And, this X is basically is X1 up to Xn. And then I have Y, which is Y1 to Yn. So I can simply minimize this, and find beta, least square. It has closed form. I can find beta, so I can fit a line. Now suppose that instead of line, this is my data, for example. And if I compute this, I can find a line here. Suppose that instead of line, I would like to fit a quadratic function to my data. What can I do? Is there any suggestion how to fit a quadratic function? So a simple trick that you can do is to extend your X and you extend your beta. Okay? So a linear function has this form. A quadratic function has this form. Right? See, I have a coefficient for x squared. If I expand my x, I have x1 to xn, it's d by n. I make a new x, let's call it, I don't know, x, whatever, x1. x1 is 2d by n. So I expanded in this form that, this is my x1. The first d rows of this matrix is d1. The second d rows, I just make each of these x's squared. Each feature x squared. So x1 to the power of 2. I wrote it this way because I mean element-wise. If it's not clear, for the moment, I assume that x is just a scalar. It's x1 to xn, so it's 1 by n. So I make x1 to be x1 squared, x2 squared, and xn squared. So I had 1 by n, I make it 2 by n. But in general, when you have d by n, you can make it 2d by n. Okay, so here that I had beta x, in the case that it was 1 by n, beta usually is d by 1. So in this case that it was 1 by n, it was just a scalar. One scalar times all of this, right? Now I have a vector 2 by 1. So here basically I had a beta as a scalar. Here I have like beta 1 and beta 2. Okay? So, so if I take the transpose of this, like beta 1, beta 2, multiply by this matrix, see what's going to happen? It's beta 1x1 plus beta 2x2 x1 squared. Beta 1x2 plus beta 2x1 x2 squared. It becomes quadratic, right? So I can define a new x here, a new beta here, when x has been expanded from d dimension to 2 dimension to 3D dimension to whatever d dimension. And beta has been expanded also. Then do the linear thing. Okay? So basically, we can learn our linear regression or linear fitting in a new domain, as if these are like new bases. And then you are fitting your linear model in this new basis. A linear model in a basis that you have x squared as some basis is quadratic in the original case. I mean, if you think of like Fourier transform, for example, wavelet, all of them are going to be the same. You know, you are learning this in a new domain. You know, you are expanding x in the case of Fourier. You are expanding x to a domain such that the bases are sine of x and cosine of x and sine of 2x and cosine of 2x. And the wavelet is another domain and so on. But then eventually you're learning a linear function there. Okay? So you can do this everywhere. And you can do this in classification. You're, instead of doing QDA, you may want to extend your x. So you have your x's, take the squared of your x's as well. And you have d-dimensional data, make it 2D. You want to have cubic, make it 3D, and so on. And then do LDA there. Then in original space, it's going to be quadratic or cubic or whatever degree that you like. Okay? Any question? Okay. So we are done with LDA and QDA. And I'm going to start a new topic. So this new topic is not explicitly about classification. It's about representation learning and a specific model for representation learning or feature extraction or feature learning. There are many different names we are going to discuss quickly, which is called principal component analysis. PCA. How many of you have seen PCA before? Okay. So principal component analysis, or PCA, is a method of dimensionality reduction. It can be used for feature extraction or representation learning. Why do we talk about PCA in a course that is about like classification? Because it's quite important how to represent data points. You know, in the first lecture, if you recall, I had a couple of slides that I showed you. For example, when you want to classify digit 2 versus digit 3, you can use raw data the images, just pixels of images as raw data, or you can map them in a new space. If you recall, there was a two-dimensional space such that this two-dimensional representation was more meaningful for making distinction between these two data. In that particular example, that new space was a space generated by PCA, Principal Component Analysis. So we're going to talk about PCA and some other technique for representational learning, how to learn a representation for a data which is useful for classification, how to represent the data, how to extract features from the data such that these features are meaningful, informative for classification. Okay. So PCA is a method of dimensionality reduction as well. So it's a method which classically is used to reduce the dimensionality of data. You have data in d-dimensional space, and PCA take them to a new space such that they are p dimension, such that p is usually way less than d. But you can do this in a way that you don't lose much information. So I would like to reduce the dimensionality of the data such that we don't lose much information. Okay? So let me start with this. It's my favorite example. Look at this green points. Okay? Just forget about this piece of paper for the moment. Just concentrate on points. What's the dimensionality of each of these points? 3. They're 3-dimensional points, right? Because you can express each of these points by x, y, and z. So if I ask you the question again, what do you think about dimensionality of these points? You can say the dimensionality of these points are 2, right? Because it can be expressed by x and y. So what happened is that, I had points in 3-dimensional space. But what happened is that all of these points are on this piece of paper. More technically, all of these points are in a submanifold of this space. If somehow I find this manifold and then I unfold it, if the dimensionality of this manifold, which is called intrinsic dimensionality, if the dimensionality of this manifold is less than the dimensionality of the space, then I have reduced the dimensionality of the data without losing much information. So basically, I didn't change the geometry of this point that much. Still, I have the information of the points, but I can express these points in lower dimensional space. Okay? This is a field by itself, how to reduce the dimensionality of the data, how to find this submanifold, how to unfold it. Okay? So a very specific case of this scenario is when this submanifold is not really a nonlinear manifold, it is a subspace, it's a linear. So all of the points in 3-dimensional space are close to a linear manifold, or more precisely, to a subspace of this space. But this subspace has a lower dimension than the original space. Intrinsic dimensionality of this subspace is less than the original dimensionality of the space, and you would like to find the subspace. So that's what PCA is, and we're going to see how it works today. So conceptually, any question about PCA before we mathematically derive PCA? Okay. I'm going to show you a couple of slides about, the terminology that we are going to use in PCA and the concept of PCA, and then we are going to mathematically derive PCA and see how we can compute it. But suppose, before I do this, suppose that I have some points in two-dimensional space. There is no linear subspace such that all of these points are on that subspace. Similar to this example that I showed to you, all of these three-dimensional points are in a two-dimensional subspace. In this two-dimension, there is no one-dimensional subspace. One-dimensional subspace would be a line. There is no line such that all of these points are on that line. Okay? But there is a line such that these points are close to that line. Not exactly on that, but they are close to that one. This line. Okay? So in PCA, actually, we are going to find this line. We are going to find this subspace such that the points are either on that subspace or close to that subspace. Okay? And we are going to call this direction first principal component. Technically, first principal component is a direction of data, is a direction in the space of data which captures the maximum variation of the data. If I look at this set of data, consider all possible directions. This is the variation of the data in this direction. The variation of data in this direction is way less. The variation of the data in this direction is less than this one. Okay? So I'm searching for direction that captures the maximum variation of the data, and I call that direction first principal component. That's identical to the geometric interpretation that I just gave to you, looking for a subspace that is basically, such that all of these points are on that subspace or close to that subspace, they are the same. So I'm looking for direction such that it captures maximum variation. I call it first principal component, or I call it, in our notation, we show it by U. The second principal component is direction which is orthogonal to the first one. And captures the second maximum variation of the data. So this is maximum variation of the data. This is second maximum variation of the data. So PCA can be seen also as sort of rotating the coordinate system. I have data in this coordinate system. PCA rotate this data to a new coordinate system such that my main coordinate is in the direction of maximum variation, second one is in the direction of second maximum variation, and so on. Okay? So a couple of general concepts about PCA. So as I said, PCA is a method of dimensionality reduction that by the way, I lost my clicker the other day. If you find it, let me know. I just borrowed this one. Okay. So principal component is a method of dimensionality reduction. It's also called feature extraction because we are extracting features from raw data. So, and we are going to use these features for classification, for example. We can use it for regression. We can use it for any type of modeling, you know. So it transformed data from d-dimensional space to a new coordinate system of p dimensions, as I showed you over there, such that p is less than d. Usually it is way less than this. You know, we can reduce the dimensionality significantly using this technique. So the goal in PCA is to preserve as much of the variance in the original data as possible in the new coordinate system. See, as I told you, you know, here, you know, I can decompose my variation of the data in two directions. Suppose that I want to reduce the dimensionality of the data to 1. I'm going to get rid of the second one, and I'm going to project everything on this subspace, you know. That would be my new data. So definitely I lost some information, but the amount of information that has been lost through this process is minimum compared to any other line. You know, if I choose this line, I'm going to lose more information. So if I want to go from 2 dimension to 1 dimension, that's the best way to go, because I'm going to lose less information. So the goal is to preserve as much of the variance in the original data as possible in the new coordinate system through this process. So when we have points on d dimension, d variable, so we think that there's a linear subspace with dimensionality lower than d, such that all of these data points are are close to that subspace, or they are on that subspace. If this is not the case, the principal component analysis is not going to help. You know, if all of my data points are uniformly distributed in this space, so you can't reduce the dimensionality with PCA. So there is no linear subspace such that all of these data points are close by. Okay. So this new variable, or this new directions, is called principal components. And the technique is called principal component analysis. So we usually denote principal components by U1, U2, up to UD. So there are D dimensions of D principal component for D dimensional data points. You know, here I had 2-dimensional data, and I have 2 principal components. In general, if I have D-dimensional data, I have D principal components, and we show it by U1 to UD. And we're going to use P of them. We are going to ignore some of them. Here, for example, we can ignore U2 and project everything to U1. In general, I can pick the first P1 and project my data to the first P principal component and get rid of the rest. Okay? So as I said, the first principal component has the maximum variation, and the second principal component has the second maximum variation of the data. And here is the most common definition of PCA. And PCA, by the way, is more than 100 years old. It's quite old technique. And interestingly, you know, more than 100 years ago, we knew how to find a subspace that captured the maximum variation. And there was an open question that how we can capture the, you know, if the data is not linear, if it's not on a subspace, but it's on a submanifold, how we can find that submanifold. Since 100 years ago, you know, we didn't have a good solution for this up to 2000. So the case of linear was clear. The case of nonlinear was not quite clear until 2000. And in 2000, there was 2 papers published in Science, back to back in the same issue, 2 solutions to this problem, 2 solutions to the case of nonlinear were published in the same issue of Science back to back. local linear embedding, and isomap. So the problem that didn't have solution for 100 years, all of a sudden had 2 solutions, and then after that, many other solutions. Okay, so that's the most common definition of PCA. For a given set of data vectors, when you have n of them, the P principal axes are those orthogonal axes onto which the variance retained under projection is maximal. Okay. Okay, I'm going to assume that I have data points in D dimension, and I'm going to assume that I have n of them, which I showed this by a capital X. So I have x1 to xn and data points. And I would like to compute U1. I would like to compute first principal component. So the first principal component, U1, which is a vector. Okay. By definition, U1 is a direction such that the variance of the data on that direction is maximum. Means if I project the data on that direction, then it has maximum variation, right? So how can I project my data point on U? U is a vector that is unknown for the moment to me. I'm going to project all of my points to U. You know, U is D is X is D by N. U is a vector 1 by D. If I make this multiplication, it's going to be 1 by N as I projected all of these points on the direction of this U. So they're going to be N one-dimensional data points. But what I'm interested in is the variance of points after projection. So I project all of these points in this direction. Then I'm looking at the variance of these projections. Because I'm looking for U. U is unknown. Don't forget that U is unknown. I'm looking for U that maximize this variance. Okay. So what would be the variance of U transpose X? Okay. Say it again. Sorry, I didn't hear.
The distance of the points from the vector U.
The distance of points X from vector U. So this distances would be the variance of projected points. You know, see, these are points. U transpose X means this point. You know, I project everything on this line. Now I'm looking, I would like to compute the variance of this point. You know, let me put the question this way. You know the variance of X. Suppose that you know the variance of X. If I multiply X by a constant, or let me go one step even before that. You know, I have all of my points, X. If I multiply X by a constant, how does the mean of this point will change? Sir? The mean will be multiplied by a constant, right? What about the variance of this point? Same? So if I have the variance of this point, if I multiply this point by a, the variance will be multiplied by a squared. You know, the variance will be changed quadratically, right? So that was in one-dimensional case. You have exactly the same thing in higher dimensional space. In higher dimensional space, if I linearly transform all of my points, the mean will be transformed linearly by the same linear function. But if I change the point change the point using this linear transformation, the covariance of the matrix will not change linearly, it will change quadratically, the same as one-dimensional space. So basically, if S is sample covariance matrix of X, then the variance would be U transpose S U. S is D by D. This is D by 1. This is 1 by D. So the variance of the, so you can just check your first course in statistics, and definitely in the appendix of the book you see all of this formula for like linear transformation applied to a data, how the mean will change, how the variance is going to be changed quadratically. You're going to see that. So if I apply a linear transformation to my data and look at the variance will be, the covariance matrix will be changed quadratically. And it can be written this way. So the final value is a scalar, 1 by d, d by d, d by 1. But if I know the covariance matrix of X, I can compute it this way. So that's going to be the variance of data after projection. So if I project my data points on U, that would be the variance. Now, among all possible U, there is many U here. Among all possible U, I would like to find the U which maximize this variance. So here is my optimization problem. Maximize this variance, which is U transpose S U. My unknown is U. Okay, S is known, sample covariance matrix. U is unknown. I'm looking for U which maximize this quantity. Okay, so what would be U? What is the U which maximize this quantity? You have a matrix, a symmetric matrix, S. And I'm looking for U such that U transpose SU is maximum possible value. I think you had a suggestion.
I think you get the signal decomposition of S.
Okay.
And then basically you transform U so that's basically the unit sphere.
Mm-hmm.
And then you just take the first component as the largest one.
And that would be U?
Yeah.
Okay. So one suggestion here. Yes? Okay. Mm-hmm. Okay. Let me ask a question. Is there any upper bound for U transpose SU? Upper bound in a sense that can you say that it can be more than this? That's the maximum. I claim that there is no upper bound here. This function has no upper bound. Any U that you give me, and you claim that maximize this, any U. I multiply this U by 2. So then this quantity is going to be twice more. So any U that you're going to give me, I can extend this U. I can change the length of this U as much as I like. And it's going to be larger. So there is no upper bound. So this is an ill-defined problem. You can't maximize U transpose SU. There is no maximum. So we have to make this problem well-defined first, and then solve. Okay? There are two, basically, degree of freedom here. There are two basically, two different things which can contribute in the value of this U transpose SU. One of them is direction of U. If I change direction, U transpose SU will change. And the other one is the length of U. As I said, it's ill-defined because I can change the length of U. But really, I'm not interested in the length of U. What I'm interested in just direction. I would like to find the direction such that if I project the data on that direction, it has maximum variation. As long as you give me the direction, I don't care what the length of U is, If you tell me that is the U, if you multiply this U by any number, still I'm happy, because I know the direction, I don't care about the length of U. So I can basically limit the length of U. I have these two degrees of freedom. I can limit one of them to make the problem well-defined. So I can add a constraint to my optimization problem. So U transpose SU has no upper bound because U can be as long as I want. Let's put a constraint here. Limit the length of U. So I want U to be like unit vector. I'm searching in the space of all unit vectors, not any vector. So maximize U transpose SU subject to the constraint that U transpose U is 1. So it's a unit vector. Okay, now how can I approach this problem? I have a constraint optimization problem. Maximize an objective function subject to a constraint. In general, how do you approach this problem? Maximize fxy subject to the constraint that gxy is a constant, for example. Sorry? Lagrange. I have to find the Lagrangian, or I have to write the Lagrange multiplier, right? So basically, Lagrangian, I can write a new function by defining a dual variable. My variable here is x and y. I can define a dual variable like lambda and write Lagrangian. Now I can take derivative of this Lagrangian and set it to 0. And I'm going to find saddle point. Saddle point is a point which make this derivative equal to 0. A saddle point, the point that put this derivative to 0 means, the derivative of fxy minus lambda derivative of g xy is 0. It means that derivative of fxy is the same as derivative of gxy multiplied by a lambda. Means tangent and at this point, tangent of f is the same as tangent, is parallel to the tangent of g. So if g is, for example, this constraint, and you want to maximize f, there is a point such that the tangent to F is the same as tangent to G. And that's your point. You know, you are maximizing this subject to this constraint. The solution is where the function and the constraint touch each other, but they don't cross. So the point that they have the same tangent. So we write the Lagrangian, take the derivative of Lagrangian, set it to 0. That's the solution, okay? So we have to do the same thing here. I would like to find the solution here. I will write the Lagrangian. So my unknown is u. I define a new constraint, which is, a dual variable, which is lambda. So the Lagrangian would be u transpose S u minus lambda u transpose u minus 1. And now I have to take derivative of this Lagrangian with respect to primal variable u. If I take derivative with respect to dual variable, I get my constraint back. So I have to take derivative with respect to primal variable, set it to 0. Take derivative with respect to primal variable. U transpose SU, what's the derivative of U transpose SU with respect to U? Sorry? 2 US. It's quadratic, right? Like x squared is 2x. Minus lambda U transpose U, which is the derivative 2 u lambda or 2 lambda u, because lambda is a scalar, it doesn't matter. And I have a term here, lambda, derivative with respect to u is going to be 0. So in my web page, there is a link to some matrix trick in linear algebra. Just go there, look at the derivative part. You know, in this course, quite often we need to take derivative of matrix functions that contains matrices, vectors, trace of matrices, determinant of matrices, and we would like to know how to take derivative of that. Always consult with that note on my web page. You can find derivative of everything, every possible cases there, because in one hand it's trivial, in the other hand it's quite tricky. You know, it's very easy to make a mistake in a transpose. It's very easy to write U transpose S instead of US, for example, or SU instead of US. So take a look at that. So this derivative is going to be 0. I mean, I have to solve for the case that the derivative of Lagrangian is equal to 0. And so it means that US sorry? No, it's supposed to be SU, I think. It's supposed to be SU. So it's SU equal to lambda U. S is a matrix, sample covariance matrix, which is a noun. U is an unknown matrix, vector, sorry. Lambda is our dual variable and U is unknown. So what can you conclude from this? A matrix times a vector is equal to a scalar times a vector. Sorry? Eigenvector and eigenvalue, right? Means that U is eigenvector of S and lambda is eigenvalue of S. That's what eigenvector and eigenvalue means, right? You have a linear transformation that you multiply to a vector, but what this transformation does is to change the length of this vector. So it's eigenvector of that matrix, eigenvalue of that. So this, I can conclude that U is eigenvector of S, and I can conclude that lambda is eigenvalue. Okay. So let's get back to our problem. I wanted to maximize this. I realized that if I find eigenvector of S and eigenvalue of S, I have a saddle point. And if it's saddle point, it should basically be a solution here, should maximize my cost function and satisfy the constraint. But there are many eigenvectors. If S is d by d, there are d eigenvectors and there is d eigenvalues. And all of them are saddle points. Any eigenvector and any eigenvalue of S is going to satisfy this. I mean, it's going to be a saddle point of Lagrange. Which one should I choose? I want to maximize it. You know, these eigenvectors are not the same. They're d different eigenvectors. Which one should I choose? Which one of these eigenvectors is going to maximize this? Sorry? The one which maximum eigenvalue. Why should I choose the one which maximum eigenvalue?
Because actually, first we didn't want to consider the length of the U, but now lambda tells us the magnitude of that eigenvector. How important is that?
Well, the magnitude of all of these eigenvectors are going to be 1.
Yes, but it is concerned in lambda, not in U.
I mean, lambda doesn't tell us the length of U. The length of U is 1.
It tells us how
Important?
not so important, yes, but it tells us that it's somehow numerize the importance of that vector.
Mm-hmm.
Isn't the eigenvalue proportional to the variance in the rescale?
It is, yeah, but how do we know that? You know, I mean, you know that because you know about PCA, but you know, suppose that you are inventing PCA from scratch now. How do you know that the variance correspond to variance, to eigenvalue?
Can we substitute the equation we got into the original
Here?
the formula? Yeah, that one. Substitute it in that first line so that we have the square of lambda times the times 1 actually.
Mm-hmm. Great.
Yeah, so we want to choose the biggest lambda.
Great. Very good answer to my question. You know, we know that for any eigenvalue and eigenvector, SU is equal to lambda U. So let's substitute lambda U for this SU here. So that's my quantity. The quantity that I wanted to maximize was U transpose SU. But I know SU is lambda U. So for any set of eigenvector eigenvalue, U transpose lambda U would be the value of this objective function. And lambda is a scalar, so it's going to be lambda U transpose U. But U transpose U is 1. So it's lambda. So for any set of U lambda, any set of U lambda is a saddle point and satisfy, I mean, my Lagrangian, set my Lagrangian to 0. But the thing is that for any set, the value of my objective function is going to be equal to corresponding lambda. So when I put it here, it becomes a lambda. So if I want to maximize this, I have to go for U, which has maximum lambda. So the solution is, so the first principal component is the eigenvector of S that has maximum eigenvalue. So we want to find the first principal component, easy. You have given X. Find covariance matrix of X. Find eigenvector. The eigenvector corresponding to maximum eigenvector is your first principal component. Is the direction that if you map your data in that direction, it has maximum variation. With the same token and same sort of argument, you can prove that the direction which maximizes the second maximum variation of the data, or second principal component, would be the second eigenvector. I mean, eigenvector corresponding to the second eigenvalue and third and fourth. So PCA is easy. Find S, do eigendecomposition. And you have D eigenvectors, order them according to eigenvalues, and they're going to be first, second, and third, and the last eigenvalues. Any question? Okay. See you on Thursday.